Okay, so we're continuing our discussion of the Taylor polynomials today, and we didn't even say what they are yet. In this specific section, we're actually going to have an introduction that's about an hour and a half long, and only then will we write the actual theorem. It's going to take a while to get to the theorem because I want to show you how it suddenly shows up. It's a mouthful of a theorem. So we're building towards it gradually. So this is what we started doing last time. We said, okay, suppose we have a function, and we're looking at the point 0, just for simplicity. We'll do it at any point later. So we're looking at the point 0, and we drew the tangent line at x equals 0, assuming, of course, that the function is differentiable. And the tangent line has the following equation. It's determined by the derivative at 0, which is its slope, and the tangent point. So when x equals 0, y at 0 has to be f at 0. And you plug in 0 here, and you see that that's exactly the case. So that determines the tangent line. And we also said that it approximates the function in the following sense. If you look at the difference between the function and the tangent line, as you get closer and closer to 0, as x approaches 0, this difference goes to 0. And in the picture, you can actually see that. The function in blue and the tangent in orange get closer and closer as you approach the point. Everybody with me? Okay, so we're picking up from here. I want to show you that, in fact, the property that we see here of getting closer and closer to the function itself as we approach 0 can even be strengthened in the following sense. If we look at the difference between f and the tangent line and divide it by x, we will still see that that goes to 0. So let's first see that and then say what it means. So I'm going to write f. Then I'm going to write y of x, which was that thing. So it's minus f prime 0 x minus f at 0. This is the numerator. And now I have to divide that by x. So dividing by x, I get f of x over x minus f prime 0. Oops, I forgot to turn off my cell phone today. Wow. Sorry about that. Okay, sorry about that. And when I divide this by x, this goes away, and here I get minus f of 0 over x. So do you agree that this is precisely this difference divided by x? Good? Now what happens when x approaches 0? F of x over x, I can rewrite this. Okay, let's rewrite this. Let's do one more step. This equals f of x minus f of 0 divided by x. And I'm going to write it, instead of just dividing by x, I'm going to do this magic trick and write it divided by x minus 0. I can do that, right? Minus f prime at 0. Now, what does all this approach when x approaches 0? What is this thing? This is not 0. This is not the derivative at 0. This is, when you take the limit of this as x approaches 0, you get the derivative. Do you agree? So the limit of this entire thing as x approaches 0, this approaches f prime of 0, this is a constant, so the limit of the whole thing is 0. Okay? You can't just replace this by 0, but in the limit you can. Clear? So what does this mean? Not only does the difference go to 0, meaning that the function and the tangent line get closer and closer, even when you divide by x, it goes to 0, meaning that it goes to 0 faster than x. Remember last time when we discussed examples for l'hôpital? Last time, some examples we did were like an exponential function divided by a polynomial. Remember that? Yeah. And we said, what does it mean that the exponential divided by the polynomial, when we go to infinity, the rate that the exponential goes to infinity is faster. It beats the polynomial. Remember that? Same phenomenon here. When you approach 0, in the limit, this goes to 0 faster. So even when you divide it by something that goes to 0, it wins. Okay? So it's not just an approximation in this sense, it's an approximation in a stronger sense, this sense. Clear? Good?
Why we did that? Do you know when?
Why did we do this? That is still to come. Okay? Okay. So, pause a second. What did we show? We showed that the tangent line in orange is an approximation to the blue line, which is the function, near the point, in the sense that the difference between them tends to 0 as you get closer and closer to 0, and in the stronger sense that even when you divide by x, it tends to 0. Okay? Now, let me give you an example. Okay? So let's take, for example, and we're going to study this example further as we proceed. So our example is going to be the very nice, friendly function f of x equals sine of x. We all know what it looks like. Let's draw it really quickly. So sine of x looks something like this. Right? So this is sine of x, and I'm only drawing the part of it which is near 0. That's all I'm interested in right now. Maybe let's draw just a bit more so you recognize it. Okay. Now, if this is f, what is f prime? Cosine. And what is f prime at 0? 1. Do you agree? Good? Okay. What is f at 0? 0. So the tangent line to this function is y of x equals f prime of x times x, 1 times x, plus f at 0. So this is the tangent line. Do you agree? Everybody? Okay. So let's draw it in orange. There it is. And not surprisingly, it looks like a pretty decent approximation for the function. Okay? So this is y equals x. And this is the tangent line to the function at the point x equals 0. Do you agree? Okay. Now, I want to somehow exhibit how I can see that it's a good approximation. Okay, just by plugging in some values. So, if, for example, you want to know what is sine of pi over 4. You want to know what sine of pi over 4 is. So this is a specific point for which we know the answer, right? We know the precise answer. What's sine of pi over 4? Right, it's root 2 over 2. But suppose we didn't know it. Okay? So suppose we don't know it. So we can say, okay, let's look at the approximation, y equals x. And then we would say, okay, a good approximation for sine of pi over 4 is the tangent line at pi over 4, which in this case is just pi over 4. Clear? A good approximation for the value of the function at the point is the value of the tangent line at the point. And since the tangent line is just the point itself, it's this. Okay? Now, if you plug in these values into your calculator, you will see that pi over 4 itself is something like 0.707. And then there are some more numbers after the decimal point. And sine of pi over 4 is 0.785, dot, dot, dot. So it's a reasonable approximation to take the value of the tangent line at the point. It's a reasonable approximation. It's not accurate. Okay? So depending on how accurate you want to be, okay? So if, for example, you want to plant 5 trees, and you want to plant them in something that resembles a circle, and you want to know the value of pi over 4, for some reason, I don't know what, this may be sufficient. Okay? If you want to send a missile and you want it to carry a satellite to place it into orbit at a specific point around Earth, you don't want to do approximations like this. Okay? You probably won't get where you want it to. Do you agree? So depending on you prescribe the what is a sufficient accuracy for you, and depending on that, you can say, is this sufficient or not? Okay? So the idea here is that the function sine, it's a neat function. We know many things about it, but there are many things that we don't know. For example, before the age of calculators, how would you know, for example, what is sine of 1? Not of nice values of pi that you know because of the trig ideas, like sine of pi over 2 and sine of pi. How much is sine of 1? Not clear, right? So methods like this would enable you to do approximations. Sine of 1, well, it's approximately 1. Okay, because it's approximately the tangent line at 1. How close is that? Well, there are 2 more boards we have to fill, and then we're going to erase them and start over. We're just building the theory. Okay? So we want to approximate by things we can handle more easily, like linear functions. This is a linear function. The tangent line is always a line. It's a linear function, right? But sometimes it's not good enough. So we say, okay, what's the second best thing after a linear function that's still manageable, that we can still calculate easily and work with nicely? Constant? Well, a constant is too good to be true. Approximating a function by a constant, right, a polynomial. Okay, a polynomial is, well, this is a specific polynomial, but polynomials of higher degrees are still nice to work with. They're easy to evaluate at specific points, right? They're easy to add. They're easy to multiply. They're easy to take derivatives of, right? So they're very manageable. It's nice to work with polynomials. And that's what we want to do. We want to approximate using polynomials. This is going to be the approximation using a polynomial of degree 1. If it's not sufficient, we're going to say, hey, maybe we can use a polynomial of a higher degree and get a better approximation, and that's precisely what we're going to do. So that's the idea. By the way, how do we know that sine itself is not a polynomial? Maybe sine is a polynomial. The fact that we write it as sine of x and define it via these triggish ideas, maybe it's a polynomial of degree 17. Could it be? No. Why not?
It's, how do you say, it repeats itself.
It repeats itself. The term for that was periodic, but why does that say that it's not a polynomial?
Polynomial always approaches somewhere in infinity.
Okay, so the more precise statement, you're right, the more precise statement would be that sine has infinitely many roots. Do you agree? And a polynomial of any degree has finitely many roots, as at most n, which is its degree. Do you agree? So sine is not a polynomial. Okay? Okay, so here's a wild guess. Maybe we'll, yeah, I'll draw a different picture. So here's another picture. Here's sine again. Same function, sine. This is sine of x in blue. And I'm going to take the polynomial, which is going to look like a wild guess. I'm going to take the polynomial x minus x cubed over 6. This is a polynomial of degree 3. Do you agree? And I'll draw it for you, and if you have a graphic calculator or a computer, you can draw it and see what it looks like. It looks something like this in orange. Something like this. Okay, so in blue is the sine function, and in orange is the polynomial. It looks like a better approximation than this y equals x line. Do you agree? Let's erase all this extra data that's kind of blurring the picture. Do you agree that it looks like a better approximation? And it's a better approximation in two senses. First of all, it sits kind of more closely, more tightly on sine. Okay, so if you were able to zoom in and look at it, you'll see that it is closer to the graph of sine itself than y equals x. And moreover, it's approximating it, it's close to it on a bigger zone. Even further away from 0, it's still close, whereas y equals x, they kind of depart somewhere here. Do you see that? Okay? So this is a better approximation, this polynomial of degree 3. Okay? And if you were to plug in values, like we did previously, so remember that we said that sine of pi over 4, if you take its decimal writing, we said it was, what, 0.707. Is that what I wrote? I think I may have... Yeah, I may have written the opposite previously. Please correct that in your notebooks, okay? This is sine of pi over 4, and pi over 4 itself was 0.785. Okay, correct that in your notebooks. But now, when I try to approximate it using this polynomial, so I should get pi over 4 minus pi over 4 to the power 3 divided by 6. And when I plug all this into my calculator, what I get is 0.705, ... So it's a better approximation. The error is only of the magnitude of what? 2 over 1,000, right? Whereas previously the error was 8 over 100. Do you see that? Is it clear? Questions? So this is a better approximation. Okay? How did I get it? How did I find this mysterious polynomial that seems to do a better job at approximating sine? And can I do... Trial and error is not the right answer. The right answer is that I looked on my papers. It's written here. Okay, but how did it... Okay. So how did I get it? The answer, this is going to be the Taylor polynomial of degree 3 for the function sine. Okay, so we need to show what are these Taylor polynomials and how we find them. So somehow there has to be a property of this y equals x that makes it a good approximation. And it turns out that that property is, I mean, what are the properties of the tangent line? What determines the tangent line? Right. It has a slope, which is determined by the derivative at that point. Right? And it goes through the point. That's it. That determines the tangent line. Do you agree? Okay. So we want to kind of extend that. So let me write some words, because I've been saying a lot of things, but let me write some stuff. So under certain conditions, every theorem has conditions, and we're going to see what they are. but for now we're keeping them vague. Under certain conditions on f near x equals 0, we will be able for any epsilon to find a polynomial. A polynomial, which we're going to call temporarily just p of x, such that the function, well, the wishful thinking would be that f of x equals p of x, right? That would be the best approximation. It's not an approximation. But obviously that cannot happen for a general function, right? Most functions are not polynomials. Okay? So it's f of x is going to be equal to p of x plus what we're going to call r of x. R of x is going to be the remainder, the error, what's left over. Okay? And this is going to be a good approximation in the sense such that f of x equals p of x plus r of x, and r of x in absolute value is less than epsilon, near x equals 0. No, this is just a vague statement of what is later going to evolve into the actual theorem of what we're trying to do. Okay? So we're going to have to establish some conditions, and those are going to have to do with requiring differentiability, sufficient differentiability. And under those conditions, you give me an epsilon. Epsilon is how much error do you allow? That's epsilon. Okay? And I'm going to be able to produce a polynomial such that the function is almost that polynomial. It's the polynomial plus something, but that something is at most epsilon. Clear? Is the idea clear? Okay, so that's what we're trying to do. And the way to do that is trying to pinpoint those properties of the tangent line that made it a good approximation to an extent, and try to extend them and see what general polynomials will follow those properties and do better. Okay? And the properties are, as we said, so the idea is the following. The tangent line satisfies two properties. One, that the value at the point 0 is precisely the value of f at the point 0, right? It goes through f of 0. Do you agree? And the slope of the tangent line, y prime, this g is a y. Okay, this is y prime at 0 equals f prime at 0. Do you agree that these are precisely the properties of the tangent line, and they determine the tangent line? Yes? Okay. So what would be a natural thing to require, for example, from a polynomial of degree 2, if we want it to be a good approximation? What would be a natural thing to maybe try?
The second derivative.
Right, the second derivative. Okay. So in general, so the tangent is a polynomial of degree 1. For a polynomial of degree n, we want a polynomial of degree n for any n which we will call Pn of x, n is going to be the degree, with the property okay, so let's write it here, that Pn at 0 equals f at 0. Pn prime at 0 equals f prime at 0. Those are these two properties. And we want to continue this for any n. So Pn prime prime at 0 equals f prime prime at 0, etc. So until, what's the highest derivative we can go if it's a polynomial of degree n? Right, so P, or maybe let's write it. Okay, let's write it like this. Pn nth derivative, remember this notation for the nth derivative? At 0 coincides with the nth derivative of f at 0. Okay? So this is our way, our attempt at generalizing these properties of the tangent line to a polynomial of degree n. For a tangent line, a polynomial of degree 1, we wanted it to coincide with the function at the point, and for the first derivative to coincide with the function, with the first derivative of the function at the point. For a polynomial of degree n, we want all n derivatives and the polynomial itself to coincide with the values of all the n derivatives of the function at the point.
Pn is the tangent line.
No, Pn is now what we're trying to define. For n equals 1, it's going to be the tangent line. For n equals 1, you stop here, and then it's precisely the tangent line. That's the polynomial of degree 1. For n equals 3, I somehow want to obtain x minus x to the power 3 over 6 for sine. Okay? So I'm going to get a bunch of polynomials. Okay? For any degree, I'm going to get an appropriate polynomial satisfying these properties. So that's my requirement. That's what I want to satisfy. Okay? How do I find the polynomial satisfying this? That's our next goal. Is everybody with me? Is everybody following the gradual build up towards the Taylor theorem? Yes?
Why do we just look at the point 0?
That's what I said. I'm doing everything at the point x equals 0 for simplicity. Everything we're going to say extends to any point A in general, and when we write the general theorem, we'll write it for a general point A. This is just for simplicity. Okay, so let me tell you how we find, given a function, how do we find polynomials satisfying this? So in order to prescribe a polynomial, what I need is to tell you what its coefficients are, right? If I tell you the coefficients, then you know the polynomial. And it turns out that there is a very, very easy to state relationship between the derivatives at 0 and the coefficients. There's a correspondence between them, and it's given by the following, let's erase this. It's given by the following, let's call it a lemma, or a proposition. Did we use the word lemma so far? So a lemma is it's a theorem actually, but it's kind of a small theorem that is usually like an auxiliary fact used in proving a bigger theorem. That's called a lemma. Okay? But some very important lemmas throughout history are by far more important than other theorems. So it's not a very precise cutoff between what's a lemma and what's a theorem. This is going to be a lemma. So let Pn of x be a polynomial of degree n. And let's write it so we can see its coefficients. So I'm going to write Pn of x equals, and I chose to call them betas, the coefficients. So it's beta 0 plus beta 1 x plus beta 2 x squared plus dot 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 all the way up to beta n x to the power n. Okay, that's the general form of a polynomial of degree n. Do you agree? Okay. Then, for any k between 0 and n, for any k between 0 and n, the kth derivative of Pn at the point 0 equals beta k times k factorial. So if you know the beta k's, you know the derivatives at 0. And if you know the derivatives at 0, divide by k factorial, you know the beta k's. Okay? So if I prove this, suppose I prove this. Okay, so this is another way of saying, let me rephrase this thing. This is another way of saying that beta k equals Pn, kth derivative at 0, divided by k factorial. Do you agree that this and this is precisely the same statement? Okay. So if I prove this lemma, and it's going to be a 3-line proof, not hard, then if I want a polynomial with these specific derivatives, right? Because let's look at the previous board for a second. That's what I'm prescribing. I'm prescribing the derivatives in terms of the derivatives of the given function, right? Somebody gives me a function. I know what f at 0 is. That determines Pn at 0. I know what f prime at 0 is. That determines Pn prime at 0. I know what the second derivative is at 0. That determines the second derivative of Pn at 0. So somebody gives me the function. I know its derivatives. Those determine the derivatives I'm looking for to have for the polynomial. Back to this board, I plug them into this formula here, and I get the beta k's. I get the polynomial. Yes?
You plug in the terms of the derivatives.
I plug in all the derivatives of f, because I want these to equal them. And then I get the beta k's. Okay? So let's first prove this, and then we'll just define these to be the Taylor polynomials, do a couple of examples, show in particular that we get x to the power 3 over 6, x minus x to the power 3 over 6 for sine, okay, and see that they actually do the approximations that we want. So proof of this lemma, proof. So if we differentiate the polynomial Pn of x k times then let's see what happens. We take a polynomial, we differentiate it k times. Okay? Do you first of all agree that all the terms of degree less than k die? Do you agree? Beta 0 dies after the first derivative. Beta 1x dies after the second. So all the terms with degree less than k die. Okay? Then, so 3 things happen. The first bullet is all terms of degree less than k are 0, or I don't want to write die. That's not a nice word. What do I write? Vanish. Good. Vanish. Do you agree? Poof. Vanish. Okay. What about the nth? What about the kth derivative of the term that is precisely of degree k. Okay? So there's a term here, beta k x to the power k. Do you agree? So for beta, not b, for beta k x to the power k, that's the term with precisely degree k, we get, what do we get when we differentiate this k times? We get k beta k x to the k minus 1. That's after the first derivative. Then k minus 1 goes down, and we get x to the k minus 2. Then k minus 2 goes down. Right. We get beta k, k factorial. Do you agree? Does everybody see that? Okay. And what remains are terms, for terms of degree higher than k, of degree greater than k. What do we get? Suppose we take a term with degree higher than k. We're going to get, after differentiating k times, there's still going to be a surviving x. Do you see that? And when you calculate it, when you evaluate it at 0, it's going to vanish as well. Do you agree? So maybe not 4. Terms, all terms of degree greater than x vanish, not entirely, but vanish at x equals 0. Yes?
If n approaches infinity.
No. There's not any limit statement here. N does not approach infinity. N is fixed. Let Pn of x be a polynomial of degree n, number. Okay? Do you agree to this statement? Okay? We're going to discuss what happens when n approaches infinity. Those are going to be called, I'm going to say words that we don't know yet, Taylor series, later on in the course. Okay? For now, n is a fixed number. Do you agree to all these facts? So, terms of degree less than k vanish. Terms of degree greater than k vanish. The only thing that survives is this term precisely of degree k, and that's what we get after differentiating k times. So at 0, we get precisely this. Do you agree that this proves this lemma? Questions? Okay. So what did we find? We found that a polynomial written like this as we're used to in terms of coefficients is actually determined by its derivatives, by all its derivatives of orders 0 through n, where 0 is the value of the polynomial itself, and all its derivatives at 0 determine the coefficients, and vice versa. If you know the coefficients, you can calculate the derivatives. Good? Okay. So with this at our disposal, now we can finally define the Taylor polynomials. So, let's go back to this board. Remember, we're looking for a polynomial satisfying these properties. Okay? So, what polynomial is going to satisfy these properties? So, conclusion, if we want a polynomial satisfying these properties, and we know how to find the betas via the derivatives, then we know how to find the betas via the derivative of f. So conclusion, define beta k to be the nth derivative, the kth derivative, the kth derivative of the function f kth derivative at 0 and divide that by k factorial. If we define the beta k's as follows, then we know by the previous lemma that the polynomial we get is going to satisfy precisely these conditions. Does everybody see that and agree with that? Can you tie up the facts that showed up on the board? Yes. This is what we want to satisfy. Okay? We want a polynomial that satisfies this. Okay? The way to achieve it is fix the coefficients as follows. Define the first coefficient to be the value of the function at 0 divided by k factorial. The second coefficient, beta 1, to be the first derivative of f at 0 divided by 1 factorial, and so on. Okay? You get betas. What do they satisfy? If these are the betas, by the previous lemma, look at this board, the betas satisfy this. Right? So if they satisfy this, the way we defined them, we get precisely this equality. Does everybody agree? Okay? Good.
I still cannot see how with that big we can get all the coefficients that satisfy this thing.
Now it's just saying that this and that are the same. I mean, cancel the k factorials.
I didn't understand this one, and I'm still drawing from that one.
Okay, if you didn't follow precisely the proof of the lemma, we can talk about that again later. Okay, I don't want to go back to that. But believe the lemma for now. Do you agree that if I define the coefficients like this, they will precisely satisfy these n plus 1 equations? Good? Okay. So here's the definition. Here's the definition. Pn of x equals. Now, okay, before I write the definition, okay, let's write it for the point 0 first, and then we'll generalize. Okay, so f of 0 plus f prime at 0 divided by 1 factorial plus f prime prime at 0 divided by 2 factorial. F prime at 0 divided by 1 factorial times x plus f prime prime at 0 divided by 2 factorial x squared plus, bless you, dot dot dot, f nth derivative at 0 divided by n factorial x to the power n. So I just wrote a polynomial x squared all the way up to x to the n, and I took its coefficients to be these. Okay? So this polynomial is called the Taylor or, oh boy, I don't know how to spell this, Maclaurin. Ooh, I'm in trouble. Okay, I'm not going to spell it too hard. In general, it's called a Taylor polynomial. Okay, and this is the very general term, even when this is not 0, as somebody asked here before. Okay, specifically when it is 0, it has a specific name that is used alternatively, and it's called the Maclaurin polynomial, but I don't know how to spell it. I'm going to do it with 15 mistakes, and it's only 7 letters. So I don't want to do that. Maclaurin.
I think you already had most of it.
Most of the mistakes I already had?
No, you spelled it right so far.
Yeah, but is it an E or an I or is it a U? I know it starts with M. Okay, the Taylor polynomial. The Taylor polynomial of degree n. This thing has the longest name in this course. The Taylor polynomial of degree n of f near x equals 0. So all of this is its name. Just saying the Taylor polynomial doesn't say enough. You have to say the Taylor polynomial of which function. You have to say near which point you found it. And all we did so far was near 0. And you have to say of which degree, because of different n's you get different polynomials. So it's the Taylor polynomial of degree n of f of x near x equals 0. Okay? And what we know that it satisfies, okay, we know, by the way we constructed it, we know that it satisfies these n plus 1 equations. It coincides, the polynomial, and all its derivatives of degree 1 through n coincide with the function and its derivatives of degree 1 through n at the point 0. Only at that point. Okay? Do you agree? Okay, so we constructed a polynomial. Our motivation was to somehow mimic or extend the phenomenon of satisfying these for 2, just for the function and its derivative, giving a pretty good approximation in terms of the tangent line, trying to extend it and getting polynomials which we now hope we can be able to show that they're even better approximations. That's what remains to do, right? So just the fact that we constructed them doesn't mean they're of any use, right? So that's what we want to do now. Before we do that and state that, let's do a couple examples. Let's calculate some Taylor polynomials, okay? And let's start with the function sine of x. So let's erase this. So example 1 of calculating Taylor polynomials, let's take f of x to be sine of x. So what do I need to do? It's very technical. I need to find all the derivatives, calculate them at 0, divide by k factorial. Those are going to be the coefficients of the polynomials. Okay? So let's start calculating derivatives and evaluating at 0. So f of x is sine of x. F at 0 equals 0. Good? What's f prime of x? Cosine of x. So what's f prime at 0? 1. What's f prime prime of x? Minus sine of x. Therefore, f prime prime at 0 is 0 again. What's f third derivative of x? It's the derivative of this, so it's minus cosine of x. So the third derivative at 0 equals negative 1. Is everybody following? Do I need to write the fourth derivative? What's the fourth derivative? Right, the derivative of minus cosine is sine again. Therefore, the fourth derivative at 0 is again 0. And then, do you all agree that from now it's going to repeat itself? Okay, so the next one is going to be cosine, and therefore the fifth derivative at 0 is going to be 1. And allow me to write dot, dot, dot at this point. Do you agree? So for the function sine, what is P1 of x? The polynomial of degree 1 corresponding to the function sine near x equals 0. You have to look back. I'm going to walk all the way to this side. Look at this formula for the Taylor polynomial, which is written here. Please look here a second. This is the formula. and we just have to plug in these values that we calculated. If we want P1 of x, that means n equals 1, then we stop here, and we get f0 plus f prime 0x divided by 1 factorial. We get the tangent line, of course. So we just get, remember that f of 0 on that board was 0, f prime was 1, so we just get x. Do you agree? Okay? I'll write that in a minute, but since we're here, what do we get when we try to find the polynomial of degree 2? That means stopping here. We need to add this term. What was f prime prime at 0? 0. So it adds nothing. So the polynomial of degree 2 for sine is still just x. And it doesn't do any better than the polynomial of degree 1. Do you agree? What's the polynomial of degree 3? We need to add the third derivative at 0, which was minus 1, divided by 3 factorial, which was 6, times x cubed. Do you agree? So let's write that. So P1 of x was x, just by plugging into that formula. P3 of x is the well-known, since we met it before, x minus x to the power 3 divided by 3 factorial. Good? Did everybody see how I got this? Okay? Okay, I don't want to go to that board back and forth, because I'm going to drive me and Yair crazy, who's filming us. So let's write the formula again. Let's see if I remember it. No peeking. Pn of x equals f at 0 plus f at 0 was 0 plus f prime at 0 divided by 1 factorial times x. F prime at 0 was 1 divided by 1 factorial is 1, x. So this is P1. Now I want P2, I add the second term, f prime prime at 0 divided by 2 factorial x squared. But f prime prime at 0 is 0 for this example, so this doesn't add nothing. Well, it does. It adds 0. Okay. Now I want the polynomial of degree 3, so I add f, third derivative, at 0 divided by 3 factorial times x cubed. That's this. Good? Question?
How do we know where to stop? How do we know that that's a polynomial and not f of 4?
You don't know where to stop. You decide where you want to stop.
Oh.
If you want P1,
If you want to keep,
that's it. You stop at n equals 1.
and the more you go, the more accurate it gets?
That is, the question was, the more you go, the more accurate it gets. That's going to be part of the discussion to follow. Okay, we didn't write the theorem yet. Remember, I promised you there's going to be a long intro today. We still didn't write the theorem. Okay, we just defined something and we're starting to calculate it, and we still don't have a precise statement of how useful is it. Okay, so the statement of does it in fact get more accurate, a better approximation as n gets bigger? The answer is, for good situations, yes. Does it get more accurate as you get closer and closer to 0? The answer is, under the conditions of the theorem, yes. Okay, but we didn't write those things yet. Okay, we still have to do that. Okay, so if we're at it, what is P5? What is P5 of x? It's going to start the same way, but now there's going to be a term of degree 4 and a term of degree 5. What's the term of degree 4? Becca, you tell me. What's the term of degree 4? Plus. I'm not going to write it. Fourth derivative at 0, which is what? 0. So P4, we don't need to add nothing, right? So we need the fifth one. It's 1, so what is it going to be? It's going to be plus 1 over 5 factorial, which is what? So it's 3 factorial, which was 6, times 4 times 5. 4 times 5 is 20, 6 times 20, 120. Good. So it's x to the power 5 over 120. This is P5 of x. Do you agree? And we can go on. Obviously, the even ends are not going to contribute anything, but the odd ends are going to keep contributing more and more terms. Okay? Let's draw. Let's draw. So here's, right here in the middle, remember we had, this was P1. We didn't call it that before, but this was P1. And this was P3. Right? Let's draw P5. So P5, if you draw it, what you get is that P5, in fact, looks like, so here's sine in blue again. This is sine of x. And P5, which we just found, x minus, okay, we'll draw it and then write it, turns out that P5 looks something like this. So it rides on sine like this and only departs somewhere here. So it's kind of something like this. So this is P5 of x, which was x minus x to the power 3 over 6 plus x to the power 5 over 120. It's even tighter, it's even closer if you zoom in, and it remains closer on a bigger interval than P3. Okay, even P3 kind of started to branch off of sine somewhere here, whereas this is still close even after you pass the maximum here. Clear? And if you do this same sort of evaluation, so sine of pi over 4, the real answer, in quote marks, if you plug it into the computer, is this. If you do P5 of pi over 4, namely you calculate pi over 4 minus pi over 4 cubed over 6 plus pi over 4 to the power 5 over 120, what you will get for P5 is 0.70714, whereas if you take 2 more digits of this, you get 1, 0. So if you are willing to go as far as P5, your error is only at the 5th digit after the decimal point. You're getting pretty accurate. Okay? Clear? Everybody? Questions? Yes?
You have to specify that this is only between on a certain interval, or because after
Good question.
5,
Good question. It's gonna be in the theorem. Okay? We didn't write the theorem yet. Okay? What I wrote here is just a value at a specific point. Okay? So in the theorem, we're going to see, and we're going to discuss it. That's going to be after the break. We're going to discuss exactly how does the n determine our situation, and how does being close to 0 determine our situation. Both, of course, have an impact. Okay? So let's take a break now and continue in 10 minutes.